All right, I'm going to get started.
How was it?
It was very packed.
I want to.
I saw that live.
I kind of have. Let me make sure I have the camera set right. Sorry.
So no Bill Nye?
No Bill Nye today.
What if I played just the introduction?
Do you want to do karaoke?
Maybe I could get behind that.
You know there's karaoke in the bar next to my house?
So we all go to the bar next to our house and do karaoke.
Okay. All right. So today I think we're gonna have kind of a shortened class today because we're actually making really good time through the material. And I want to introduce two equations today that are corrections to the ideal gas law, and I want to talk about them a little bit. And we'll do some calculations just to get you oriented with these equations. We'll talk about the physical basis for them, and look at just some graphs. That might only take us like 45 minutes, and then we can go home. I had kind of an interesting idea last in the other section. I'm going to draw it's something for us to think about a little bit. So, yes, last class we talked about the Leonard-Jones potential, which looks kind of like this. All right, so this is the potential energy. Call this atom. Well, I'm just going to pick a neon atom. I like neon. And we're going to ask the question, how much are they attracted or repelled each other as a function of their distance? And of course we came up with this nice model, right? It's the Leonard-Jones model, the LJ model, where V of R, 4 epsilon sigma over R to the 12th minus sigma over R to the 6th. And I'll just represent what those mean. The depth of the well, basically the strength of the attraction is minus epsilon. And the point in space, the distance where the energy is minimum, a point of the most attraction, is at R equals the 6th root of 2 times sigma. Right, and on homework, you'll actually derive that. These two values right here, these are what they represent. I want to talk a little bit about how, right, this is what we call potential energy, right? The idea is that as two neon atoms come together, they basically store some energy inside of them, right? So imagine that they're sitting here at this point where they're at the maximum or the minimum of their energy. It takes epsilon energy to break them apart, right? In order to go from here to here in energy, or from here to here, however you want to think about it, you have to pump in epsilon amount of energy to break that bond, right? So the idea is that negative potential energy which is V, negative V implies attraction, right? Right, that means when you have a negative V, it means you have to supply a positive amount of energy to break that attraction. And a positive V means the opposite, right? So when you break a repulsive when a repulsion breaks apart, you gain energy, right? The system loses energy because it's now going from positive to less positive, right? Repulsion. Okay. Now the interesting thing is that this is just potential energy, right? Our neon atoms also have kinetic energy, right? And we said that the kinetic energy, right? This is one of the things that we kind of learned with the ideal gas law, is that the kinetic energy for a given set of particles, right, is on the order of 1/2 mv squared, which is proportional to the gas constant times the temperature. There's actually a factor of 3/2 here, but we won't worry about that. We'll talk about that on the homework. But the average I'll just write that here. The average kinetic energy of an ideal gas is 3/2 RT. Okay, so basically there's always on average, this much kinetic energy in your atoms or your molecules. And so if we're at non-zero temperature, right, let's say we're at room temperature, then there's always some kinetic energy left over, right? There's always some kinetic energy in our system. And the question is how does the kinetic energy compare to our potential energy scale? So let's say, for instance, T is 300 Kelvin. We'll use the regular version of R, which is 8.3 roughly joules per mole per Kelvin. Let's just say that's 8, just to make it easy, right? Let's just say it's roughly 8. So that means then that the average amount of kinetic energy is 3/2 times 8 times 300, which is, let's see, that's 2,400 times 3/2, so that's 3,600. So it's 3.6 kilojoules per mole. All right, so at 300 Kelvin, these molecules or these atoms have roughly 3.6 kilojoules per mole of energy, always, from kinetic energy. So the question is where does that kinetic energy fall with respect to this potential? So for instance, you'll have to forgive me, I'm going to use purple here, but it doesn't matter so much. Imagine that 3/2 kT puts us at this energy. Or RT, sorry, we're using RT here. Right, so the system, if there was no kinetic energy, 0 Kelvin, right? They're completely frozen in place at this position. The energy of the system is here, it's negative, right? Right, and so, but then you can add the kinetic energy, and maybe there's enough kinetic energy to put us here, right? So the system is on this amount of energy. Notice that that's not enough energy, right? You still need to put additional energy into the system to break the bond, to break the attraction, right? In order to separate our neon atoms, we need to go a little further, right? We need to go that amount to break it apart, okay? But we don't. But that, of course, this is all generic, right? We don't actually know. It depends on the attraction how strong this is or not. But what if RT was up here? What if the system has enough kinetic energy that its energy is up here? Well, then the system's never going to end up down here because it always has enough kinetic energy to break apart. Right? There's always enough residual kinetic energy that if it's ever in this region of space, this distance between the two, it's always going to have enough energy just to fly away. Okay? And so that means then that there's always a balance, right? For very, very weak interactions, say for 2 helium atoms, right, the epsilon for helium, 2 heliums is on the order of 0.084 kilojoules per mole. If we're at 300 Kelvin, the amount of kinetic energy is way stronger than the potential energy, right? So basically the 2 helium atoms on average at 300 Kelvin are barely going to touch or get sticky together, if you will, because there's always enough kinetic energy just to fling them away, right? They're just moving too fast to get stuck together. Okay, they're not ready to settle down yet. But you can imagine that as T goes down, right? As temperature goes down, forgive me that I use T and T here. That's an unfortunate coincidence. Imagine that the temperature, for instance, is at 1 Kelvin, right? Or 4 Kelvin or something like that. If the temperature was 4 Kelvin, then we'd have 3/2 times 8, which is 12 times 4, which is 48 joules per mole. Right? And that's competitive with this. Right? This is the same as 8.4. No, sorry, no, it's not. This is 100 joules, 10 joules. 84 joules per mole. Right? So at 4 Kelvin, there's not enough kinetic energy to overcome this attraction. So at 4 Kelvin, you would expect that the helium atoms would converge together, right? They would stick together in this potential, right? They'd get stuck in this energetic well, and you can't really treat a helium at 4 Kelvin as an ideal gas, because in fact the most attractive orientation of 2 helium atoms is bonded together at this point. So the idea of ideal gas, there are different limits to the ideal gas approximation. It's good when the average distance between two atoms is large, or two particles, an equivalent way of saying this is either that pressure is close to 0 or volume is close to infinite, right? Right? If you have an infinite volume, then the distance between two atoms on average is infinite. Or temperature is very high. And the reason why a high temperature gas is a good ideal gas is because it has enough kinetic energy to overcome, basically to cancel out all the potential energy of attraction. Right? It's interesting that when you think about the average kinetic energy of a helium atom, the kinetic energy starts to be competitive with the attraction, the potential energy of the attraction between two heliums around 4 Kelvin. There's no surprise about that because that's the temperature where helium condenses into a liquid. Helium condenses at about 3.6 or 3.8 Kelvin. Right? So that makes sense. When the potential energy of attraction is so great, so let me write that. When attractive potential energy overcomes or is stronger than the kinetic energy, we get condensation, if you will. Right? Our helium atoms in this case look more like combinations of helium atoms, right? A dimer instead of it being individual atoms, right? And you can think of the critical limit of that, right? If you take that idea of helium being attracted to itself and not having enough energy to break apart thermally, that once you get to the logical conclusion of that, well, you think liquids, right? Liquids would be the logical kind of end idea of this Lennard-Jones potential, right? Where you have so little energy that the system can't move out of this attractive zone, and eventually you get to so low kinetic energy that the system transitions into a liquid state. Okay? So the interesting thing, this kind of gets us into this idea of a real gas. One of the things that we're going to learn is that an ideal gas is just a gas. It doesn't matter what temperature you're at, what pressure, what volume, it's always a gas, no matter what molecule you have. But a real gas is one that can liquefy, right? And the idea of liquefaction, kind of like in terms of energy, is this idea where the residual kinetic energy of the atoms or the particles in your liquid is so low that it can't overcome the attractive potential energy of the attraction between two species. Right? So as you cool, the system gets deeper and deeper in this well, and harder it is for it to get out of the well, and so eventually the whole thing's going to condense into a liquid. Okay, we'll learn about that. But here's the problem: is that the ideal gas law, in that sense, does not predict liquefaction, condensation. An ideal gas is always an ideal gas at every temperature. So that's a problem because obviously there are many liquids. Every gas has usually has a point where it liquefies, right? So we need a theory to predict that. Questions so far about this? It's weird. It's like there's like sometimes when you like on mountains that have really high cover in one direction. Tree coverage in one direction and a lot of sunlight in the other direction. All the trees grow in one direction. That's what this room looks like right now. You guys are all like this at the moment. So the idea now is that we need to come up with a model for a gas that also allows us to predict that a liquid will form. Okay, that's the real problem. So that's what we're going to do today. I'm going to erase this for now and start over here. So a man named van der Waals had a really great idea. He says, let's come up with a theory to improve the ideal gas law. Let me make sure I have the equation available here, since I didn't bring my notes. Yeah, great. Van der Waals has a great idea. He says, let's relax some of the ideal gas approximation and see what we can do. And so he does two things. He says, one, right, just as we learned, assume particles are attracted to one another And 2, assume particles have a size, an average size, if we will. Assume particles have an average size. They're not points anymore. Have a physical shape. Okay? So let's think about the parameters of our gas, our box, and what will happen to them if we start to assume these two assumptions. Let's assume now the particles are attracted to one another. So let's look at one. Let me write this in black now. Let's look at one now. Okay, let's take an ideal gas. All right, we start with an ideal gas. What happens to when we start to allow particles to get attracted to each other? What do we think happens to the volume of our gas?
Reduces.
What's that?
Reduces.
Decreases. Right? Volume decreases as particles attract each other, right? Because they're going to stay closer together, so they're more compact. Likewise, what happens to our volume if the particles have a physical shape or a size? What happens to our volume? Yeah, it increases. Right? We have two different competing effects. Right? Because now you can't fit as many particles in a unit area because they've got some shape. Right? You can only pack them so deeply because before they start touching, shape increases, shape size. I was going to say as they get more thick, but that's not really a good way to put it. Shape size as shape increases or size increases. Right? So we have two competing effects here. Attractions and size. And van der Waals was very aware of this, right? These are not particularly complicated ideas to think about. And so what he does is he says, okay, well, let's correct the volume for size and attraction. Okay? And the easiest one to think about is the size increase. Okay? So let's say we have a volume, a molar volume. Right? This is volume over moles or liters per mole. Right? It's useful to think about this because it's a size-intensive property, molar volume. And think about what happens. How can we correct? Hold on a second. Am I confusing these? Yeah, sorry. Is B in there again? Do I have these mixed? No, okay, yeah, no, I'm right. Okay. Right, so I've got something flipped in my head and it's driving me nuts now.
It's okay, take your time.
Yeah, okay. Let's think instead. Let's tackle this a slightly different way.
I think it's because you're starting with 2 when you're talking about 1. Because particles have a physical shape, but you're pointing at 1, which is
No, I understand that. But the corrections that I want to make to volume are contradictory in my head at the moment. But that's okay. Instead, let's think about it in a different way. Let's say that we want to correct the volume. Let's say we want to correct the volume for physical size. Okay? Right? So we want to take volume for an ideal gas, a molar volume for ideal gas. So remember this is volume over moles. And we want to go to a real gas, and we're going to consider about the size of the particles. All right, we're going to start with 2 here, right? And the idea is going to be we need to correct this by some scale factor, right? Because we need to account for the fact that some of the volume of our space is being held by molecules. So I want to think about volume as, maybe it's useful to think as the volume in a gas is the space not consumed by matter, right? This free space, if you will. Okay. Maybe this helps us a little bit, right? So this actually changes our results, right? So if we think of volume as the free space that doesn't have a particle in it, right? So when a physical object, when a physical object goes from a point to a mass, or to something of physical size, the volume actually is going to decrease if we think about it this way, because there's more volume free space being taken up by the particle in with its physical size, right? Let me explain that a little better, right? So here's our points, right? Here's our ideal gas, your points, right? And volume, our measure of volume is the free space, right? Which is every inch and nook and cranny of this except for the exact points where the gas particles are, right? This is our free space. Right, this is an ideal gas. Right, but when we make our atoms have a physical size, right, the amount of free space decreases because some of that volume is now taken up by the particles, right? Right, this is a real gas. Right, so if we think of this volume as V, the free space in an ideal gas is V, then this is going to be V minus the size of the molecule, which we'll call B, times the number of particles, the moles of particles. Right, B is our correction, our size factor. Right, so each particle has a physical volume that fills up some space and are in moles of those particles. So the total volume of our system is now V minus NB. Does that make a little more sense? Okay, so let me change this a little bit. So let's, instead of calling volume increases and decreases, let's say that the free volume increases as particles attract, and free volume decreases as particles get bigger. All right, so it's the opposite logic. Instead, we're thinking about the system, not just the particles themselves. Right, so when you make up a physical size, the molar volume of your gas is smaller than you would expect because some of that space is being filled up by the atoms themselves. So that means that V real is going to be V ideal minus the number of moles times some constant B. Okay, this is our scale, our size factor, scale factor, if you want. We'll just call it size factor. B. Now, what are the units? Well, the units are the units of volume here, right? Logically, right? So the units of B are liters per mole. Okay. Now we have the other thing is attraction. Let me just rewrite this here. So this is physical size. And this is V minus NB, and this is V. Ideal gas. Let's do the same thing now for attractions. Let's now consider a gas of V minus NB, right? A gas that has balls instead of points, but they aren't attracted to one another. Right, so that's this case. So we go from here to here. And our free space is this area. Now we want to include attractions. Right, now what happens is that now the volume is, the free space is going to increase because the average distance between the two particles will decrease, right? There's more free space because the particles are more closely spaced, more closely together, closely packed. Right, so we can draw that like this. So we can just instead draw them like pairs or triplets or whatever you want to do. Right, they're much more closer together. So that means that the molar volume will increase. But the interesting thing is that attractions are not attractions are a two-body problem. Right? You need to have two particles or two volumes, two particles, if you will, to have an attraction. So, as we described, the physical size decreases the volume by a linear factor in the number of molecules, or linear in volume. But because this is a two-body problem, where you have to have attractions between two physical bodies, this is actually proportional to v squared. This is a square because you have two particles, v times v, if you will. Right, so in fact, what the correction to this is a new constant a over v squared. And the units of a, which I'll write over here, they're corrected by a factor a over v squared. Right, it's an increasing factor where a, the units are liters squared per mole squared, effectively. Right, because you need to have two bodies, right? So we have two factors of volume coming together, right? Because you have to have two bodies hit each other. Okay, so there's a linear correction to volume, which decreases the volume because of size. And there's a quadratic factor that increases the volume. But it's, as you can imagine, it's a much smaller effect because you now have to rely on two bodies coming together instead of just one body existing, right? So B is going to be larger than A most of the time. This is a smaller effect. So van der Waals had this nice idea, right? And so he came up with an equation. Let me keep erasing here. Van der Waals says, okay, so I have a linear correction in volume for particle size and a quadratic correction for the attraction of two particles, right? Quadratic because there's two, not one. And so he comes up with a really lovely equation. This is what's called the van der Waals equation. All right, and if you look at it, it looks very similar to Pivner, right? You have P times a factor in P, V equals RT, right? And because this is molar volume, the factors of N go away. There's no N here. We can convert this into volume, and you get a factor of N over here. All right, so this is just the ideal gas equation, but we've corrected for attractions, and we've corrected for the size of the particles. All right, and I'm just going to give you an example. Hopefully I have some numbers here. I know I have some numbers here. Yeah, so for methane, for instance, I do have methane here. I forgot to put in my book of list of van der Waals coefficients. You can look them up on Wikipedia. A measures the attraction of two methane molecules. And the units of this are The size of this is 2.3026 liters squared. And what are the other units? Liters squared bar over mole squared. Mole squared. Okay. And B, for instance, is 0.043367 liters per mole. Right, so let's just look at these numbers real quick. They don't really mean anything, they're just numerical values, but we can kind of get a physical sense, right? The idea is that for every mole of methane you have, your volume decreases by this much, right? So the methane molecules, a mole of methane molecules in some way take up somewhere on the order of 4.3 milliliters. That's the idea here, right? This number is a little harder to understand. A, right? This is the term that's for the attraction, right? So A for attraction. And what's a term for that starts with B for size?
Bigness.
Bigness? Yeah. I was going to say big boy, but I like bigness. Bigness. Yeah, that's the bigness coefficient. Right? And so it's kind of hard to interpret the 2.3 number because you also have this factor of pressure, right? And that makes sense because the higher the pressure, the more likely that you're going to have more attractions because they're closer together. So this number is a little hard to predict exactly, but it gives us a sense that if you take the square root of it, square root of A is on the order of, what is that? Square root of 2.3. God, I don't know. It's like 1.2, 1.1. Right? It's like a small correction. It's about 10% at 1 bar. So it's about a 10% of correction at 1 bar, roughly. Right, so it's a small change. You can imagine that as you get to higher and higher pressure, that gets worse and worse, right? It's linear in pressure, right? So if this contribution gets twice as big as pressure goes up by a factor of 2.
1.5.
1.5, thank you. So it's 50% correction. Roughly. This is a very, very rough kind of Fermi calculation. But the idea is that this could be significant. And you can think about molecules that are very polar, like water. Actually, let me just put waters as an example. Water van der Waals coefficients, because I don't remember them off the top of my head. All right, water has, for H2O, A is 5.536, and B is 0.034. 0.049, sorry, 0.049, with the same units. Right, so water and methane have very similar sizes, right? But you can tell, well, water has much stronger attractions than methane, right? So A is much larger, right? So A kind of scales with the attractions, right? Water has hydrogen bonds. Right, so you can imagine it at 1 bar, right? We can use the same kind of idea that at 1 bar on 1 liter, take the square root of A, and you're getting, that's a factor of over 2, right?
2.4.
Yeah, thank you, 2.4, right? So for water, at 1 bar, you're way, way out of the ideal gas law because this is a very large correction. Right, you have take this as P is 1 bar. What are the units here we're using? Yeah, 1 bar, right? If you take P 1 bar, this to be 5.5, and this to be 1 liter. Right, your pressure now, your ideal pressure at 1 bar is now approximately 6 bar. Because the pressure that's being exerted against the wall of your container is not just 1 water, but now multiple waters pressing against it, right? Remember, pressure is just the force being exerted against the wall by the gas particles. All right, this is pressure. And so when you have 1 water molecule, you might have some pressure, but then you have 2 water molecules that are stuck together pressing against the wall, and you have more pressure. You end up having more pressure being exerted as a function of per mole on a per mole basis. All right, so your pressure gets corrected significantly for water. Right, and of course, the weaker the particle is, weaker the attraction, the less important this is. Now, let's look at kind of roughly let's do a quick calculation. Pull out your calculators, and let's do a quick calculation. Let's say we have 1 mole of CH4, okay, of methane. Our volume, the volume of 250 milliliters. At what pressure? At temperature at 273.15 Kelvin, right? Or room temp at 0 Kelvin, or sorry, 0 Celsius. Okay, so let's ask the question: what's the pressure for an ideal gas? And what's the pressure for a van der Waals gas? Okay, so it's easy to solve for the ideal gas, right? It's nRT over V. Right, in order to solve for pressure here, we got to do a little bit of algebra. Right, so in order to calculate pressure for a van der Waals gas, we should divide both sides by V minus NB, and then subtract A minus over V squared. Right, RT over V minus NB, then we have P plus A over V squared, subtract A over V squared both sides, and we get P. So that's going to be P equals RT over V bar minus NB minus A over V squared. Right, and maybe in this form it makes more sense about the size and the attraction thing. Right, if the volume is getting small, the free volume is getting smaller because of size, and because the particles are coalescing together, the pressure drops as a factor of V squared. Okay, so we need to know a couple numbers, right? So we have everything. We have volume, we have temperature, we have moles. Remember that V bar is volume over moles. Of course, we have 1 mole, so V bar is the same as V. And you need R, right? So again, let me give you R real quick. All right, we're in bars, so you can't use the 8.3 number anymore. So R is 0.0831446 liter bar mole Kelvin. Okay, and you already have A here, right? A and B for methane. Right, use these. All right, so let's calculate this. Let's just take a few minutes. Let's look at P for both. We'll call P ideal and P BDW for van der Waals.
Professor Seifert,
Yes, ma'am.
the N in the second set of parentheses, isn't it redundant to have because V bar already accounts?
Well, you need it for the units.
In my notes from last year, it's V bar minus B, not including N.
Oh.
Wouldn't it include N if it was
yeah,
regular?
you're right. I'm sorry. You're right.
Right?
Yeah, you're right because
Okay.
this is liters per mole and this is liters per mole, right? You said we say thank you.
Okay.
Yeah,
I just
you're right
wanted to
about
double
that.
check that.
You're right about that. It's V bar minus B. Thank you.
Just before everyone started doing their
Yeah,
calculations.
thank you. It doesn't make a difference because N is
it's
1,
one,
so
right.
it won't matter anyway. But someone's got a number, you can raise your hand. What do you-
91 bars for the first one.
This one? What do you got?
91.
Yeah, 91. Let's look at significant digits. How many do we got here?
3.
How many we got here?
2.
Yeah, I guess we have 2 then. Yeah, okay, fair enough.
That's why I didn't
Yeah,
pick
fair
one
enough.
because there wasn't
Fair
one.
enough. Fair enough. All right, 91 bar, that's right. 91 bar. Well, let's see if we can do the VDW one.
I'll give it a moment. It's 90.8. So round it up.
Is that what everyone else have that number? Yeah, 73. That's a 20% difference. My high school chemistry teacher, I failed the kinetics. Well, I didn't fail the kinetics exam. We all did really bad on it in AP chemistry. And he said, he looked at our answers and he says, you can guess better. I can guess better than that. And honestly, that's what I feel about the ideal gas law in this situation, right? There's nothing exotic here, right? A mole of methane, right? Actually, it's a significant amount of gas. At a normal temperature and a normal volume, already at normal conditions, our gas is off by 20%. Right? Even though we know methane isn't very attracted to itself, right? This can make a huge difference, right? And you could even think, well, what happens, for instance, if we turn off one of these factors? Right? What happens if we say that it has physical size but no attractions? Right? That means that this would be 0, right? And you just have P equals RT V over B. Someone want to calculate that real quick? Let's do that. That's a fun question to do. All right, so let's turn off attractions. So that's P equals RT V minus B. Someone want to give me that number? $110. Now it's the opposite. Isn't that interesting? Right? If you conclude both, you go below the ideal gas limit. But when you only include attractions, you go over the ideal gas limit. Now that should make sense, right? Because now these have physical size, they exert more pressure against the wall, so your pressure will go up. Right? They're big, they're pushed further apart from each other, so the pressure will increase, right, with respect to the gas, or with respect to ideal gas. Right? So this is greater than ideal. And now let's turn off size. So that would be P equals RT V minus A over V bar squared. What's that number? After you. Right, if you turn off size, well, they can clump up as, let me put bar. Right, this is less than VDW, right? Right, you turn off size, that means they can get really close to themselves, right? They can pack up really, really closely. Right? In some ways, the size is the repulsion part of the potential, right? Because you don't want, the idea is that you don't have, the two balls don't overlap, right? They're going to hit each other, and that's all they can do. Right? They're kind of like physical spheres. Right? So we turn that off, well, they can just get real close together, right? And of course, that lowers the pressure to unrealistic numbers. Right? So this all makes sense, right? You've got to have both. Right? Particles have size and particles have attractions, and there's no reason to knock one out and keep the other one because you don't have a physical picture that way. Right? You have to have both. Now, the real answer, now, of course, I'm saying all of these things, but these are just numbers that we're just floating in the air, right? We don't know if any of them are correct. The real value is 78.6 bar. Right, so van der Waals does very well, right? Ideal gas does very poorly, right? At normal conditions. Right? You can play around with this a little bit and look at look at the ideal gas law and look at the VDW law as you lower the number of moles at a given volume or increase the volume, and you'll see that the ideal gas law improves. And VDW kind of they coalesce to the same value. Right, so if you have a gas at a very, very large volume or very low pressure or very low concentration, however you want to think about it, the VDW prediction and the ideal gas prediction are very similar. Right, but still not perfect. Right, we're still off by about 5 bar, right, a little less than 10%. But that's pretty good, right? We've made literally the dumbest possible correction we could, right? Or not the dumbest. It's actually a very clever one. We've taken the simplest possible correction, or two corrections to the ideal gas approximation, and we've improved from over 20% to less than 10% at this scale. That's not really the power of the van der Waals law, though. Right? We can calculate these, and in fact, there are other equations that you can use that predict gases just as well as the van der Waals. Different types of different types of equations. Right? I'm going to write another one down because you need it for the homework. We won't go into too much detail about it. But another one that's used very commonly in chemical engineering, is what's called the Redlich-Kwong equation. And the reason why it's good is that this equation is built for high temperature, high pressure gases. Right? There's lots of, for instance, the Haber-Bosch process, which forms ammonia, high pressure gases. You need to have, in order to form ammonia from hydrogen and nitrogen, nitrogen and water, nitrogen and hydrogen. To form ammonia, you need to be at very high pressure and very high temperature, right? And so to model that, you typically use this Redlich-Kwong equation because it's very accurate for high temperature, high pressure gases. And I'll explain why that is once I write it down. But it looks very similar, right? We have, geez, I can't read that. My eyesight's going bad. Okay, thank you. P is equal to RT V bar minus B, right? Same background, right? Same idea as van der Waals, right? We account for the size of the particle. Sorry, it's usually big B. Sorry, big B for Redlich-Kwong. And we have a different factor for the attraction side that's proportional to temperature to the 1/2 power, the square root of the temperature. V, I think it's V plus B. All right, so it's a little more complicated. So B has constants. B has units of liters per mole, and A has units of liters squared times. Let me just make sure I got it right. Liters squared per pressure per mole. Or do I have the moles at the bottom? Sorry. Yeah, moles at the bottom. Sorry, my apologies. There's two factors of moles per liter here, right? You have V times V, so there's a mole squared at the bottom, and there's a Kelvin to the 1/2, like that. So it's liter squared bar, mole squared times Kelvin to the 1/2, right? Those are the units. So you added a little temperature correction, right? And that's the idea. And the idea of that is that the attraction is a temperature-dependent quantity. Atoms, molecules that are at very low temperature, right? They don't have enough kinetic energy to break the potential energy, right? So they tend to stick together more, right? And then at higher temperatures, they have more kinetic energy, so that they can break those bonds more, right? The attraction is less effective at high temperature than it is at low temperature, right? So they correct for that. Notice that in van der Waals equation, there's no temperature dependence on traction, right? A has units of just liters of pressure and moles, right? But we know from the previous conversation, right? If you have enough kinetic energy to overcome that potential hump, that potential well, that the attractions don't matter anymore, right? Or vice versa. So the Redrick-Kwong equation adds a little bit of temperature dependence to the equation to correct for that. And that works really well at high temperature, especially with gases that have strong attractions. Like this is what you would want to use if you're using highly compressed water vapor, right? Where hydrogen bonds still play a role, but you're at high temperature and high pressure. And I'll just give you the number. We can do the same calculation with methane. So for CH4, we won't do it, but 75.3 bar. Right? That's closer to the real value. Right? It's not perfect. Right? 78.6, 7.3, but it's closer than any of them. And it turns out that as you increase the temperature, right, if we went to 1,000 Kelvin, this equation would work better than any of them because of this temperature dependence. Right? Temperature dependence basically turns on and off the magnitude of the attraction. Okay. All right, so we have about 15 minutes left. Okay, I want to look at one more thing. Something qualitative. Well, we've talked about these gas laws. These are just empirical, right? There's nothing magical about this. There's no real theory going on. We're just taking intuitive ideas on how to improve our law and correcting the ideal gas law with those improvements. Right? This one's just size and attraction. And here we have size and a temperature-dependent attraction that can turn on and off. Right? Nothing fancy. In fact, they're just empirical, right? These numbers, the A's and the B's, they're just experimentally measured. There's no real way to calculate them. I guess theoretically you could. They're just empirical values, right? It's just an observational correction to a gas. So there's nothing really special about this. But it does make a big difference, right? By just using some logic. The van der Waals equation has a much more interesting result, though. And you can't tell that until you plot it, you graph it. What I want to do now is I want to take a gas and I want to measure its pressure as a function of volume. So I'm going to make a plot, and let me make sure I have my axes correct for this. Yeah. I'm going to plot pressure on the y-axis, and I'm going to plot molar volume on the x-axis. Right? You can think of it either way. You can either molar volume again is volume over moles. So you can think of increasing molar volume as an increasingly dilute gas, right? You lower the number of moles, or increasing molar volume means you increase the volume as well. However you want to think about it. And we're going to think about how the pressure responds as you do that. Maybe a really good way to think about this is we're filling in a volume of some gas, or we're evacuating a bulb of gas along this direction. So increasing molar volume means increasingly dilute. All right, we're going to watch the pressure change at a constant temperature. All right, we can predict what this looks like for the ideal gas really easily. All right, P is equal to RT over V bar. Right. So really easy to plot. Ideal gas looks like this for different temperatures. This is ideal gas. So for instance, maybe this is 300 Kelvin, 200 Kelvin, 100 Kelvin, 50 Kelvin, and so on and so forth, right? Right, it's just a 1 over x, right? It's just an inverse function. Right, so they don't look very interesting, right? And they increase as pressure increases because, because they're proportional to temperature, right? So they go like this as you increase temperature. Now what about the van der Waals? Now we have to do some algebra to get V on one side and P on the other side, but let's just do that. Actually, I'm going to save that. That's a part of your homework. That arrangement to get this kind of plot. But what I want to show you is the plot of that, right? Pressure versus volume. So it's not immediately clear what it looks like from this expression, but I walk you through the algebra on the problem set to do it. Because eventually you're going to plot this yourself for a gas. I'm going to do the same thing now for a van der Waals gas. All right, we're going to start with high temperature. All right, well, at high temperature, it looks just like an ideal gas, right? We said that, right? We talked about that at high temperature, gases are more ideal. All right, so at high temperature, let me do it in red. High temperature, it looks a little like this. All right, let's say it's T equals 1,000 Kelvin or something like that. Oh, sorry, 1,000, right? Really high temperature. Looks like an ideal gas. What you end up noticing is that the shape of the function changes as you start to cool the gas. It starts to flatten out a little bit, and you start to get a little more shallow. And eventually you hit a temperature where there's what's called an inflection point. And it starts going like this. Let's say this is like T equals 500 Kelvin. It doesn't really matter what the temperature is. It's just an example of 300 Kelvin. Notice that now there's a different geometry to this curve. This is still V bar minus versus P. This inflection point happens. As you start to cool, what looks like a point ends up becoming a line. As you cool even more, this region where it's flat gets even longer. Like that. So instead of it just being a gas that compresses like an ideal gas, you have this region here. It's a point at one temperature, and then eventually becomes a longer and longer line, where as you change the volume, the pressure doesn't change. Right, so let's remember that this means increasing moles, increasing concentration, and this is decreasing concentration, for instance, at constant volume. So I could take it. Let's say we're at a 300 Kelvin. Let's say this is at 200 Kelvin. Right, I could be at 200 Kelvin, and I got a bulb of my gas, and I'm feeding gas into it, and the pressure doesn't change. Well, that's strange. I'm putting molecules in there. Where the hell are they going? They're not in the gas phase because the pressure isn't changing. If they were in a gas phase, if they were gaseous molecules, the pressure would increase as I increase the concentration. But that doesn't. It just stays flat. Why could that be?
Attracting.
Okay. But we know, they're attracting here as well. But think about it this way. If we know that the attractions are fairly weak, and we would expect that the pressure would increase slightly, but in fact it doesn't. I know you can't really tell from my drawing, but it can be really flat right there. So you're feeding in molecules and they're not increasing the pressure. So what do you think is happening to them? Attraction's a good thing, an idea. what kind of attraction, what is occurring though? It's not, obviously it's not a weak attraction because pressure would change. So something stronger, more dramatic and extreme is happening. Yeah,
Is
Megan.
it changing phases? Like,
Yeah, changing phases. Liquids form. So what's happening? Let's say we're here, right? We're on this curve right here, right? You start to feed in your gas, your pressure goes up. And then as you start to feed in gas, the pressure doesn't change. Well, all that's happening is that gas that you're feeding in is condensing. Right? It's condensing, it's condensing, it's condensing. Notice though, right, and notice it changes. Let me make sure I have this right. Yeah. It's actually it's more dramatic. It's more dramatic on this side than this side, so it's more like this. So it's like flat and then kind of a smooth curve off, and then a sharp up at the end. So again, as you feed in the gas, and then a liquid starts to condense. And then once your concentration gets high, your pressure skyrockets. And the reason why is, so right, this is gas here, right? And you now have liquid gas coexistence here. And now you have an almost vertical increase after this region, where maybe it's to think as you increase the pressure, the volume doesn't change. That might be a better way to look at this region. Instead of thinking that the volume changing, the pressure responding. Another way to look at this is that the pressure flies up independent of volume. And what this is doing is it's solidifying. Right? You can keep putting molecules in, increase the pressure, but the volume doesn't change. Well, that's a solid because a solid resists pressure, right? A solid doesn't deform under pressure. Right? So this curve is vertical. Right? So this is solid, this is liquid, and this is gas. Right? So by just including attractions and physical size, we've gone from a world where everything's a gas. Right? You and I don't exist. Actually, nothing exists other than gases. Right? There's no physical planets, there's no dust, there's no grains, there's no ice. Obviously no biological material, no liquid water. And then we magically give our particles size and attractions. We have to have both. We have to have both. And we suddenly now have a region, we now have the existence of other phases. Remember that we're looking at this from the perspective of the gas. So as we increase the concentration, the pressure increases. As we increase the gas concentration, the pressure doesn't increase because it condenses to a liquid. And then the pressure just flies up with no change in volume because it's just solidifying at that point. All right, so by just making these very, very small assumptions about it, we've now magically made chemistry. Chemistry does not exist. Phases don't exist unless there is physical size and attraction between all particles. Now the interesting thing is that from this perspective, right, we see the gas. This is all in the perspective of the gas. We have no idea what it looks like from the solid point of view, right? Or we don't have any idea what the liquid's point of view looks like. No idea what's going on. We only just know the difference between pressure and volume here, right? So we really got to start thinking about that as we go through. Well, what's really happening at this point? What's happening at this point, right? How does the liquid play a role? But the thing the take-home point I want to give with the Van der Waals equation, is that liquids aren't special. Liquids are just a natural consequence of gases having size and attractions. And that's all a liquid is. It's like a critical gas. Right? And that point critical is very important. Because we often call this point, right? There's a point at which the temperature gets to a point where you go from an ideal gas curve, right, where it looks just like 1 over x, to where you have an inflection point. Right? This is where the slope is 0 and the curvature is 0. We could say that the derivative of pressure with respect to volume is 0, and the second derivative with respect to volume is 0. Right? So the curvature is 0, and the pressure is 0. Or sorry, the slope is 0. This is what we call the critical point. And this is the point in a gas where the distinction between a gas and a liquid breaks down. In fact, when we start digging into this, when we get into phase transitions, we'll talk more about these critical points. But there is a region, every gas, every liquid has a point where the boundary between liquid and gas disappears. There's no difference between the two. And it turns out the only difference between the two is just a slight variance in temperature and what we call entropy. All right? And we'll talk more about that as we get deeper into thermodynamics. But at this point right here, this critical point, it's almost as if there's one volume and one pressure where a liquid might exist. This line is just a point at this point, this critical point. And this is the point where the boundary between liquid and gas breaks down. Because there's really no difference between a liquid and a gas. They feature the same things. It's just that now you have this different kind of, this discontinuity in the pressure volume, the compression, right? Things change between a liquid and a volume, and a gas, right? The compressibility of a liquid, right? It's very hard to compress a liquid, right? Take a glass of water and smash it with your hands. I don't know why you would ever do that, but you can't compress the liquid, right? It's just going to go flying. But you can do that with a gas, right? It's very easy to compress a gas, but you can't compress a liquid. But so they have very different characteristics, right? Different properties. Right? We know liquids can be very good electrical conductors, but gases aren't. Gases are terrible electric conductors. And so they have very different properties. But the thing that van der Waals tells us is that there's really no fundamental difference between the two. There's just a region, and it's just, the idea is a liquid is a critically cooled gas such that the attractive forces always overcome the gas's kinetic energy. So the idea is that now your attractions, the potential energy from the attractions is so great that now gas particles can't escape anymore, right? They can't escape. If they get stuck together, they're gonna get stuck together, and they're not gonna come apart. And that's all a liquid is. It's just a gas that's got some like energetic glue, right? So you can always tune that, right? We can always get rid of that by increasing the temperature and boiling it off. Right? Or we can change our material, make it less weakly attracting, and then the gas will exist at a higher temperature or a lower temperature than another one. Right? But there's nothing fundamentally different between a liquid and a gas, other than your energy balance between kinetic and potential energy exchange. And there's always going to be a point in temperature. There's always going to be a temperature where you suddenly go from gas phase to gas and liquid, where the liquid starts to win out. And that's what we call the critical point. All right, so there's a problem on the homework about this idea, this critical point. And ask you to calculate the critical point for carbon dioxide. When we come back to phases, we'll learn a lot more about carbon dioxide and the critical point of carbon dioxide, because carbon dioxide can form what's called a supercritical liquid. And that's a gas that's also a liquid simultaneously. There's no distinction between the two. It's a liquid and a gas simultaneously. And you can actually do it in lab. So I'll show you some videos of supercritical CO2 when we talk about it. And there's some really beautiful physics and chemistry that go along with that. But every gas has this property. Benzene, methane, CO2, oxygen, argon, helium, you name it. They have a critical point. There's a point at which the gas ceases to exist and the liquid exists, or you can't tell that, or they coexist together. Okay, and we wouldn't be able to have that without van der Waals. Okay, so we're out of time. Tomorrow, on Tuesday, we're going to switch gears a little bit. We're going to start with the first law of thermodynamics. We really haven't talked about the laws. I mentioned them in first class. We're coming back to them. And what we're going to think about is taking a system in equilibrium, in thermal equilibrium, right, at some temperature, and we want to change it, right? Maybe we want to compress something, or maybe we want to expand something. Or maybe we want to do some work, right? Maybe we want to use energy to do something for us. So we're going to dive into the physics of that and the chemistry. And that'll lead us to a lot of really interesting topics. We'll talk about, the next couple of weeks, we'll talk about air conditioners. We'll talk about internal combustion engines, which are two great chemical reactors, if you will. And we'll talk about the best chemical reactor of them all, the great thermodynamic process that defines all of us, and that's the sun. The sun is the most important and most impressive thermodynamic system in our solar system. And so we'll talk a little bit about how all this applies to the sun as well. Any other questions? So that went the whole time, I'm sorry, but you got me talking, so have a lovely weekend.
So would this be the equivalent of an air compressor having water in the bottom that you have to?
Absolutely, absolutely. We're going to talk about.
Because I know you have to like throw air compressors over so often.
We're going to talk about processes that are cyclic, where you might go in steps of compression and expansion. And
Thank you.
you're welcome. So imagine you have some compressor and some expander, and what you can show is that there's going to be a hot side and a cold side. And so you take air conditioner takes hot air in, compresses it, and then expands it. And when you expand a gas, it cools. And so when you do that, the compressor or the loop, the cooling loop, gets cold enough that it's not that the air conditioner liquefies, it's that it liquefies the water and the air around it, the hot, right. So the condensation you find in the air conditioner is not from the, sorry, you too, thank you, is not from the cycle or from the air conditioner itself, but rather the cooling process of the air conditioner affecting the air around it. Yeah, so we'll talk about that in a lot of detail. Yeah, we'll even do some calculations.
I just wonder because like I always have to empty out the air conditioner when I get home.
Yeah.
Not the air conditioner, but compressor.
Question.
Yeah.
Just because I gotta sit with it for a second, and if I gotta sit with it, I know other people
Yeah,
are
sure.
gonna have to sit with it. Shouldn't it be? Wouldn't pressure skyrocket in the gas phase, not decrease?
As a function of what? Nothing, no pressure's decreasing here. Pressure only, everything's decreasing as you decrease concentration.
Thank you.
You're welcome. Are you talking about this right here?
Yeah.
Right, so maybe it's easier to think,
I don't know why I'm having so much trouble with
it's
this
easy,
now.
because this is not a well-defined function. You're thinking like here
I'm
this is
thinking
a
like a
well-defined
regular-
function. Right, this
yeah.
breaks the vertical line test.
Right.
Right, so it's instead think of it the other way. Flip this 90 degrees.
Okay.
And you're changing pressure and monitoring volume instead.
Okay.
So as you change the pressure of a solid, which is you pressing down on it, what happens to the volume of the solid? Exactly. So think about, let's flip this around 90 degrees like this. Put volume in this direction and pressure in this direction. Increasing pressure. Right, so oh wait, no, sorry, that's not right. It's vertical. This is tough. This is tough.
I definitely have
Yeah,
to
so
sit
it's
with it
like
for a
it's
little
like
bit.
this.
Okay.
Right, so as you increase the pressure, the volume decreases in the gas,
Right.
and then as you increase the pressure in the liquid phase, the volume drops as it condenses.
Right.
Right, this is gas phase going into liquid,
Right.
this region, and then when you hit the solid, as you increase the pressure, nothing changes with the volume.
Right.
Right, so maybe it's easier to think of it the other way.
Yeah.
Yeah. I'm going to remember that for the next class when I talk about this, is to rotate
Because
this
I
90
saw some
degrees.
very confused faces too, and it,
Yeah. All right, I'll bring this up on Tuesday
Yeah.
again. Yeah,
Because
you're right.
I know we're not at like phase change like diagrams and stuff yet, but I know
Yeah,
if this is on the homework, I know I'm gonna get lots of questions about it.
yeah. The homework is more about this point right
Finding
here
the
and having them
point.
calculate it. and not this condensation
Okay.
region. But yeah, this is probably a better way to look at it. So at the beginning of class, I'll draw this again and then draw it the opposite way, and
Okay.
maybe it'll be more clear. Yeah, I think this is probably an easier way to look at it. Yeah, cool.
Yeah.
Yeah, I know it's a little confusing.
Like,
I have to sit here and think about it
as,
too.
Like, cause I saw this as like you're increasing volume. Maybe it's just because I was thinking of like an ideal gas. I don't know, but like I saw this as like if volume is increasing, then pressure would increase.
Yeah, this is molar volume, so this is
Right.
So this would increasing molar volume means at fixed moles, the volume's increasing, which means the pressure's decreasing. So it's opposite of what you think.
Okay.
Yeah.
I think it's because that's where I got tripped up. Okay.
Yeah. Yeah, it's probably easier to think of this as instead of V bar is as 1 over n instead as the variable on the x-axis.
That's what I'm
instead.
thinking.
Yeah, that's probably an easier way to do it. Yeah. All right, I'll draw this next class. That's a
Yeah.
good idea.
And I would also tell the rest of the class to think about it as 1 over n.
Yeah.
Because like volume, like I don't know, I see V and I think volume. Like I just ignore the V bar.
Yeah,
So I
yeah,
think
yeah. Okay. Good idea.
I would do it 1 over n. Because I see V and I think, okay, I'm putting like more water into my cup. Like, well, not water. Like I'm gonna pop a balloon. Like I'm putting in more volume of air.
Yeah, the idea is here you're keeping you have a tank that doesn't change in volume
Right.
and you're adding more stuff to it.
Right.
There are more moles per liter.
Okay.
Yeah. Anyway.
Alright.
Less. Yeah, you get the idea. Yeah,
'cause
I'll clarify
if
that.
I want to if I have to explain it, I want to make sure that I get it.
Yeah. You've got the right idea. I'll make it more clear next time. Thank you.